Hey guys, welcome to Unit 11. In Notes A, we're going to look at some different theories behind what can make something become an acid or a base. What's going to determine that category? So it's all about acids and bases, and then what kind of products are formed during their neutralization. So let's start off by looking at some properties of both acids and bases in this little table that compares them side by side. First, the most defining characteristic that you may be already familiar with is their taste. Acids, like lemons with citric acid, have a very sour taste. Whereas as far as bases go, that taste would be much more bitter, like tonic water, which has a chemical called chlorine in it. Makes it very bitter tasting. So sour taste versus bitter taste. They also have a different effect on indicators. We're going to get into that a lot more in Notes B when we talk about the pH scale. Some indicators are good at telling lots of different pH numbers, whereas some can just have like a cutoff point. Like, for example, litmus paper, red with an acid, blue with a base. So we're going to look at different indicators, and the idea is that they would have a different effect on those indicators. An indicator basically tells the pH of the substance by its color. So the color, of course, would need to be different if I can use that to determine acid versus base. Another important property would be a physical property like being corrosive as opposed to being slippery. So being corrosive is the idea that it would be like eating away at something. Like most of you have this idea that acids will eat away at a metal. It's not literally eating it away and to the point that it's disappearing. What it's actually doing is a single replacement reaction where the hydrogen is reacting with the metal and the metal is being pulled into solution as an aqueous compound. So we have this idea of being corrosive with metals because they have the hydrogen very low on the activity series for single replacement reactions. So they're going to be very good candidates to be able to react with metals. Bases, on the other hand, are slippery. A lot of bases are cleaners. Lye is a very well-known base used for soaps. So we've got this slippery feeling for bases. They do neutralize each other. So, of course, an acid would neutralize a base, whereas a base would neutralize the acid. And that neutralization reaction is something we're going to look at a lot today in Notes A. One last property, and you'd actually kind of see a conflict or a contrast, I should say, between what the properties are for acids and bases, but this property is the same for both. You may remember from the electrolyte section from Unit 8 that in order to conduct an electric current, all we really need is a lot of ions in solution. And so it all comes down to the dissociation factor. Strong acids and strong bases will be very good conductors or good electrolytes, whereas weak acids or weak bases would not be as good of a conductor or poor electrolytes, but still, either way, they will conduct a current because they are ionically bonded, not molecularly bonded. Those molecular compounds, remember, did not dissociate and would not conduct electricity. Acids and bases, either way, will both have ions in solution, and so they will, in some form, conduct that electricity. So these are our properties of acids and bases. The next thing we're going to do is look at three different theories, starting with the very first and most limited definition, the Arrhenius theory of acids and bases. According to Arrhenius, in order to be an acid, a substance has to contain a hydrogen ion. I do mean ion. So again, a covalent compound wouldn't cut it. Something like CH4, where the hydrogen's in the back seat, telling us that this is acting as all nonmetals. Covalent compounds are not acids. It would be HCl, which would dissociate, breaking the ionic bond, and produce this hydrogen ion in solution. Hydrogen ions are actually pretty unstable. If you think about what they really are, they have an atomic number of 1, meaning I have one little proton. They have a mass number of 1, so 1 plus 0 is all that can equal 1, meaning 0 neutrons. So there's nothing else in the nucleus. And the hydrogen atom would have 1 lone electron, meaning the hydrogen ion would be deficit that electron. So all a hydrogen ion really is a proton. And you'll hear me use those words interchangeably, actually. Proton versus hydrogen ion, because they are literally the same thing. But what happens is when we put this in a solution or in water, remember water was very polar. It had a great partial negative charge, all that hydrogen bonding stuff where it had these really strong intermolecular forces. So this is really negative part of a molecule, whereas the proton is positive. So what would you expect when you get opposite charges together? they're going to attract. And so your proton is going to join up with your hydrogen molecule, making a new type of ion called our hydronium ion, which would be H3O+. This is what happens when you combine the hydrogen ion with a water molecule. You'll get this hydronium ion. So again, in practicality, you'll hear me use all of these things interchangeably. Proton, hydronium, the hydrogen ion, because it all kind of happens all at once. The proton becomes the hydronium ion pretty instantly. It's not going to just hang out there as a lone proton. That's not stable. So when we look at formulas, when we start focusing on the math part of it, don't let this hang you up. These are kind of like the same thing. It's an automatic process, our hydronium ion. So there's another type of ion that would define our base. According to Arrhenius, a base must have hydroxide. So it's going to be, again, an ionic bond that breaks, producing hydroxide. So you're looking for this OH in the compound in order for it to be considered an Arrhenius base. You may know of other bases. Yes, this is a very limited theory, but you have to be able to determine if it fits this theory. So it has to have the OH in order to fit this definition. So when we have an Arrhenius acid and an Arrhenius base react with each other, you get a very special type of neutralization. This is actually a special form of a double replacement reaction. Compound reacting with another compound. And so you're going to get that inside-outside pairing. The outside cation and anion would combine to form water. And here my inside chlorine and sodium would combine to form sodium chloride. Don't forget to always put your cation first. Don't forget to balance your charges. It's the same old double replacement reactions from Unit 6. So the idea here is that every Arrhenius neutralization reaction will always produce water because it has to have hydrogen and hydroxide. And then it's going to produce some other salt. Remember, salt doesn't necessarily mean NaCl, it just means an ionic compound. So whatever the cation and anion are that came from the hydrogen and hydroxide compounds are then going to combine with each other to form that salt. So this is always going to happen for this Arrhenius neutralization. You're always going to form water and some other salt. So we're going to now look at what kind of net ionic equations we would get when we look at neutralization reactions for Arrhenius substances. So I have here hydrochloric acid and sodium hydroxide. Very typical acid and base. So hydrochloric acid is one of our 6 strong acids, and sodium being in the first group with hydroxide would also be a strong base. So we have these strong acid, strong base fitting the Arrhenius definition. I want to go ahead and jump into writing that initial equation before I start looking towards net ionics. So first, one reactant would be HCl, another reactant would be NaOH. And from here, I can predict products. One thing I want to mention, since I did acknowledge that these are strong, I'm going to only write a one-way arrow. If these were weak acids and bases, this would be a two-way arrow, a reversible reaction. We'll talk about that a little bit more in a minute. So let me go ahead and predict my products. So my hydrogen and hydroxide would combine to form water, H2O, and my Na and my Cl would combine to form NaCl. This is basically the reaction we were looking at a moment ago. But in order to break it down to net ionic equations, I need phases. So H2O that's formed will be a liquid form. Since we didn't take the time to memorize the precipitation rules when we were looking at solutions, I want to go ahead and work all of these out, allowing you to make one big assumption. All the other compounds will be aqueous. This will only work to get the desired net ionic equation if I do not get a precipitate in the end. So let's go ahead and assume we're dealing with aqueous substances, which will apply to my reactants as well. And yes, that is an assumption, but it's the way we're going to get to our products. All right, so the first thing I want to check is this balanced? We do want a balanced equation to start with so that we can get proper coefficients when we break it down. And I don't see any differing subscripts here, so I know that I have my balanced equation. If we did have to balance charges, you would want to make sure that you go back and check for coefficients needed as well. Now I want to go through and break up things that need to be broken up when they are aqueous and ionic. So my hydrochloric acid will break, my sodium hydroxide will break, my sodium chloride will break. The water will not. So the hydrogen and chloride ions will separate, H plus and Cl minus. Hydrogen being in the first column, chlorine being in the seventh column. So it's got a +1 and -1 charge. I don't have any subscripts or coefficients, but remember those would go here as multipliers on the number of ions. Now let's move on to the sodium and hydroxide. Sodium being in the first group also has a +1, and then hydroxide always has a -1. No coefficients or subscripts, but we would need to consider that. Then we're forming water, H2O, which is a liquid, so it doesn't break. And then I'm going to separate my sodium ion from my chloride ion. So with the net ionic equation, with the total ionic equation here, you are separating the ionic bond, you are giving the ions the appropriate charges, and any multipliers come out as coefficients. So now we're ready to cancel spectator ions to get the net ionic equation. So we see chlorine and sodium are exactly the same on both sides, so those would be our spectators to be removed. And what I have left is the hydrogen ion, and remember the final equation needs phases again. So hydroxide ion, the ions are always aqueous, and they came from aqueous substances in order to form my water. So the idea here is a hydrogen ion and a hydroxide ion will form water. This is my net ionic equation. And as it turns out, no matter what your Arrhenius acid and base is to start with, you will always get the same net ionic equation in the end, because your cation and anion from the salt will always be your spectator ions. No matter what they are, they're going to cancel out in this second step. And so the net ionic equation for all Arrhenius neutralizations that do not form a precipitate will be hydrogen and hydroxide forming water. All right, that's going to do it for everything special about Arrhenius substances. Let's look at a little bit of a broader theory, Bronsted-Lowry's theory of acids and bases. So according to these guys, an acid is a proton donor. Remember, a proton and a hydrogen ion are the same thing. And then the base would be a proton acceptor. So they're a little more open-minded. It doesn't have to be the hydroxide that accepts the hydrogen. It could be anything able to accept that extra hydrogen ion. Anything accepting the hydrogen ion is now considered a base under Bronsted-Lowry's definition. So let's look at an example here where I have hydrochloric acid reacting with water. What I want to do is compare my reactants to my products. Did the hydrogen from the hydrochloric acid go over to bond with the water, or did one of my hydrogens from the water come back to bond in the hydrochloric acid? So to answer that question, we have to look at our products. It looks like it's the water that ended up with the extra hydrogen, and the chlorine is missing its hydrogen. So that must have been my first option, where the hydrogen left the chlorine. See how it ended up all alone? And then my water is now up a hydrogen. So that must have gained it. Once I identify the proton transfer, the source of the hydrogen is going to be the acid, and the taker of the hydrogen is going to be my base. So normally we think of water as neutral because it's a 7 on the pH scale, but as Bronsted-Lowry defines it, it can act as a base. So with Bronsted-Lowry, we've got to look at where the proton transfer occurs. Wherever it comes from is my acid. Wherever it goes to is my base. Now let's look at the product side. We're going to look at something called conjugate acid-base pairs. I always think of conjugate as complementary, like left shoe, right shoe. So an acid could have a conjugate base, and a base can have a conjugate acid. And before we look at this on the product side, we can actually look at this totally outside of the context of a chemical reaction. For example, let's take water. If I wanted to find its conjugate acid, I just need for it to gain a proton. So that means I'm gaining a hydrogen ion. So H2 becomes H3, and then neutral, if I added a positive charge, would become positive. Conjugate base means that I'm going to give a proton or be down a proton. So H2 becomes just one H, and then neutral, if I lost a proton, would become negative. And that's a weird way to write hydroxide. So the conjugate acid of water is hydronium, the conjugate base of water is hydroxide. The acid is up a proton and the base is down a proton. But the difference is always exactly 1 proton, which means we get to kind of play matchup in order to find them on the product side. So when you're doing these labeling problems, first you want to start with the acid and base. Those will always be on the left-hand side, the reactants. And to identify them, you have to find your proton transfer. Wherever the proton comes from is your acid, wherever it goes to is your base. Then we're going to look on the product side. The conjugate base is going to match up with the acid, except for it would have 1 less hydrogen. Whereas the conjugate acid would match up with the base, except for it would have 1 more H. So let's try an example. First thing I want to do is find my proton transfer. So if I look at NH3 and H2O, I see I could have the hydrogen going either direction. Of course, if something doesn't have a hydrogen, it can't be the acid. But in this case, I have 2 options, so let's peek at our products here. The NH3 became NH4, so that seems to indicate that it absorbed a proton. And then the water is now down a hydrogen, seeming to indicate that it lost a proton. So it must be this top method, where I have transferred from the water to the ammonia, meaning the water is the proton donor. That's going to make it the acid. Then the ammonia is the one that accepted it, making it the base. Now let's try this product side, where we're going to label conjugate acid and conjugate base. Playing matchup, I can see that NH3 is very similar to NH4, only being different by 1 proton. It was a base, so it's going to have a conjugate acid. You can see that I've increased the number of hydrogens, making it more acidic. Playing matchup with the other substances, H2O and OH, again, they match except for that 1 proton. And I'm down a proton, making it more basic, my acid having a conjugate base. So it's complementary. The acid has a conjugate base and the base has a conjugate acid. Notice how we labeled on the left first and then played matchup to figure out what was going on the right. So conjugate acid was the ammonium ion, and then the hydroxide was our conjugate base. So in this situation, we determined water was acting as an acid, whereas our last example, we used water as a base. So water is actually able to do either acidic things or basic things. There's a special name for that. We call it being amphoteric. Water is the perfect example. Something that's amphoteric can act as either an acid or a base. It can fit either the proton donor or the proton acceptor. So that would be considered amphoteric. All right, let's look at how strong acids and bases are. What do I mean when I say the strength of an acid? Weak acids don't dissociate well, don't conduct electricity well. Like, what do I even mean by weak or strong? It all has to do with the degree of dissociation. So if I have a strong acid or base, it will completely dissociate, meaning a one-way arrow. So hydrochloric acid is an example of a strong acid. So it is going to break down into hydrogen ions and chloride ions, leaving no HCl molecules left in solution. It would become 100% ions, and that would be the strong electrolyte, good at conducting electricity. Whereas if you have a weak acid or base, it will not dissociate completely, meaning there will be some reversible reaction. So hydrofluoric acid is a good example there. The H+ and the F- ions will be produced, but that being one of the most electronegative atoms, or the most electronegative atom on the periodic table, this is gonna be re-attracted to each other, and you're going to have some reversible reaction. So here it's all ions on top, whereas I would have only some ions on the bottom. Complete dissociation, great electrolyte, because it has more ions. Weak acid or base, poor electrolyte, because some of those ions have recombined into molecules. So it's all about dissociation. Acids and bases act the same way. if they're strong acid or strong base, you have a one-way arrow with complete dissociation, whereas a weak acid and a weak base will only partially dissociate, and so you would use a reversible arrow. So how do you know if it's strong or weak? How do you know how much dissociation will occur? Well, fortunately, there are only very few substances that do go through complete dissociation, and we know what they are. So it's a short list and one I personally recommend memorizing. Hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, and perchloric acid. One more oxygen there than chlorate. As far as the bases go, it's going to have a cation from group 1 or 2, and then have hydroxide or be an Arrhenius base, having hydroxide as its anion. So if it fits these conditions, then it is a strong acid or strong base. And if it's not on this list, if it's not one of these cations, it's just not a strong acid, and so it will not completely dissociate. In some more advanced classes, they may tell you how much it dissociates, maybe an 80% dissociation, and then you're gonna have to adjust some of your answers based on having less dissociation. But for right now, I'm happy if you can tell which ones do and which ones don't completely dissociate. All right, last theory. We're gonna look at the Lewis theory of acids and bases. We've looked at Lewis something before. Think back to Unit 3. What was Lewis all about? We drew those Lewis structures with the dashes and the dots. The dots representing, and the dashes also actually representing all these electrons. So Lewis theory is going to focus on electrons. Lewis acid is an electron pair acceptor, where Lewis base would be an electron pair donor. This is kind of opposite the Bronsted-Lowry theory, but it makes sense that it would be opposite because this is focusing on electrons. It has a special type of neutralization as well. When you look at Lewis neutralization, you're going to be looking at forming a new covalent bond where the electrons come from the same donor atom. So that can be a little bit tricky. I want to look at one example here where NH3 reacts with water to form the ammonium and the hydroxide. The first thing I want to do is point out that Bronsted-Lowry theory is kind of incorporated into the Lewis theory. Actually, as I mentioned that, I think I have a document or a slide on the next page. So they're kind of built into each other. The Arrhenius is the most limited theory, but if it is an Arrhenius acid, it's also a Bronsted-Lowry. Same true for Lewis, where some things might fit the Lewis definition. If it is a Bronsted-Lowry theory acid base, then it will fit the Lewis theory here. So, oops, let's rewind a little bit. Sorry, get a little bit ahead of myself. So we can tell if we compare the NH3 to the NH4 that again, the hydrogen, just like when we looked at the Bronsted-Lowry theory, was moving over to the ammonia. So I can tell that one of my hydrogens is going to be moving towards the ammonia. Now think about this with the octet rule. Can I have just an added in H here, 4 single bonds, and a lone pair? That would be 5 electrons, which is not okay. And so the electrons have no business there. So the donor of the electrons would have to be the thing trying to make room for the proton. So where the proton moves in with the ammonia, that would make it the acid because it's a proton donor, the base accepting the hydrogen. It's also true, if you look at Lewis's definition, that that electron pair is going to move over to the water. So the proton acceptor is the electron donor. So it's still the base based on Lewis's theory, and still the acid based on Lewis's theory. So these theories do work together. They just have a slightly different emphasis. Where the Arrhenius theory focuses on having hydrogen or having hydroxide. Bronsted-Lowry focuses on donating a proton as an acid or receiving the proton as a base. Lewis's theory focuses on donating an electron as an acid, or an electron pair, I should say, as an acid, or receiving it as base. So it's kind of this give and take that connect the Lewis and Bronsted-Lowry theory. Bronsted-Lowry theory with the Lewis theory, I should say. All right, so now we've looked at what makes acids and bases unique, and we've looked at 3 different theories to classify the different substances as acids and bases. Be careful which definition the question is asking you to use. That's going to do it for your introduction to acids and bases. The next set of notes, we're going to focus all about the pH scale and calculate where it fits on that pH scale and use that to determine whether it should be considered an acid or base. So that'll be Unit 11, Notes B. We'll see you there.